All right, hey guys, welcome to week 3 of Intro to Analysis. So, as a little disclaimer, this stuff I think is really cool. So, I think this lecture is going to be interesting for you if you haven't seen this stuff already. And if you have seen it, maybe you'll get a new perspective from what we're going to talk about today. So, we're going to talk about cardinality. So, what does it mean for two sets to be the same size? We're going to talk about bijections, countable sets, and uncountable sets. Okay, so recall from the first lecture that the cardinality of a set is the number of elements in the set if we have a finite set, okay? And so I'm going to be using this notation throughout the lecture. It looks like an absolute value bar, but it's read cardinality of S. And so, if we have finite sets, we just simply count the number of elements, okay? So for this set A, B, and C, we have 3 elements, so the cardinality is 3. For this set, we have 2 to the n, such that n is either going to be 1, 2, 3, or 4. And so S is just going to be 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So we have a cardinality of 4 elements in our set. Now, the natural numbers, that's an infinite set. We can always find a number bigger than the highest natural number we can name. And so this cardinality is going to be infinite, but we're going to learn in this lecture that there's differences in infinity. And so the natural numbers are it's like the simplest infinity that we can understand. And so we call these countably infinite. Countably infinite. I cannot spell to save my life, but yes, countably infinite. And we're also going to learn that the real numbers are also infinite, but it's a different sort of infinity. It's a different sort of notion than the natural numbers, the cardinality of the naturals. And so even though this set is also infinite, we can always add more and more natural numbers to a list. We can't exactly list all of the real numbers. Like, there's no way to do that. And we're going to prove at the very end of this lecture that there actually isn't a way to do this using a famous argument by George Cantor, who went crazy because he thought about infinity too much, I suspect. So what's the lesson in all of this? It's like, well, yeah, this stuff is really cool, but if you go too far down the rabbit hole, you might end up at the funny farm. So we call this uncountably infinite. Okay, so we're going to prove some really remarkable things today. To me, they're really remarkable. Like, the idea that the real numbers are uncountably infinite, and also any open set of the real numbers is uncountably infinite, which is insane. Unless, well, I'm trying to think, is the empty set open in the reals? I don't know, we'll worry about that another time. But here's the big idea of today. There are different sizes of infinity, okay? So, that's what we're going to talk about. Okay, so this little blurb here that I wrote, we know how to tell whether two finite sets are the same cardinality. We just count the elements, right? So, in our example here, the set S, well, I named them both S, but whatever. Anyway, these two different sets in example 1 and 2 have different cardinalities. So they're not the same size. We can just count them. But what about infinite sets? How can we tell if two infinite sets are the same size? We cannot literally count all of the elements in an infinite set. We can't do it. And so we need some sort of notion for what it means for two infinite sets to be the same size. And that's where we're getting this bijection principle right here. And I have 3 stars, which means it's very important. And so we say that two sets have the same size if and only if there is a bijection between them. So remember from our first lecture, bijection means that we have an injection and a surjection, okay? And we can picture this visually in a nice way. So let's look at this example here. Very simple example. We have 3 elements, star, heart, and face. And that set's cardinality is equal to the cardinality of 1, 2, 3. And why is that? I mean, we're going to get more formal with this, but I just want to give you guys some intuition of what's happening when we get to more complicated sets. So if star, heart, and face is a set A, and 1, 2, 3 is a set B, we can construct a bijection between these guys, right? So we can send star to 1, we can send heart to 2, and we can send face to 3, and we can do this in 3 other ways to make sure that, first of all, everything over here is getting hit. So everything gets hit means surjection. This means surjection. And that there's only, it's 1-to-1, right? So injection means 1-to-1. So there's only one thing that maps to everything in B. And that's the injective part, 1-to-1. Okay, so we can clearly see that this is a bijection. All right, now this set is not the same cardinality as this set. I think your book does this, but the point is that we can never have a perfect matching. So A and B, we have X, Y, Z, and then over here we have M, A, T, H. And there's no way to perfectly pair up these elements because one guy is going to be left alone. Okay, so this thing is not surjective. So not surjective. And so these cardinalities are not the same. We can't construct a bijection from A to B or vice versa from B to A so that all of these elements get hit in B and they get hit exactly once. You could do the same thing if you let A equal math, the MATH, and B equals XYZ. That's going to force this thing to not be injective if you switch B and A. So if you let B equal XYZ, A equals MATH. So you can try that to show that that map is not going to be injective. Okay, here's something that I found on the internet that people are really riled up about. And there's not a bijection between hot dogs and hot dog buns. I don't know if you guys knew this, but apparently in the standard pack of hot dogs, there's 10 hot dogs, but there's only 8 buns. Okay, and I kind of went down a rabbit hole here, but I mean, people are really talking about this, specifically on Reddit. And so, this person says you have to buy more buns and hot dogs in a never-ending loop. And this person says you can just buy 4 packs of hot dogs and 5 packs of buns. It's 8 and 10, not some prime numbers. And I think what maybe they meant to say is that, they're not large, relatively prime numbers because, if you had 5 hot dogs in a pack and 7 buns in a pack, those are prime, but you could just find the least common multiple, 35, and say, okay, well, I have to buy, what did I say, 5 hot dogs in a pack? Well, then you have to buy 7 packs of hot dogs and 5 packs of buns, and then there's your bijection. But anyway, I thought this was pretty funny. And there's actually this article that explains why, and I couldn't get into it because there was a paywall. So if anyone knows why, and they're interested in sharing, go ahead and let me know. Okay, anyway, so that's just a silly example. All right, so let's go ahead and find the cardinality of these sets. Okay, so So here, this was the example from the previous side. We can clearly just count the elements and say that the cardinality of S is 3. Okay, same thing here. We already did this example. Cardinality of our set is 4. And the natural numbers we said was countably infinite. And the reason is that, we can, so since our set is n, we can construct a bijection from n to n, okay, sending each natural number to itself so that we have an exact pairing. One way you can think about this is if you have your top set on top, 1, 2, 3, 4, 5, blah, 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 is our natural numbers. Our bottom set is, again, the natural numbers. You can always pair these guys up in one-to-one correspondence like this. And so this is called the identity map. We're sending each element in n to itself. And so this is a bijection, okay? Nobody gets missed here. Okay. And so the order of S is the order of n, which we're going to say is countably infinite. I'm going to get a little bit more precise of what countably infinite means in a bit, but for now, let's just go through these examples. Okay, so here's our set, S equals e to the n, such that n is a natural number. Okay, so you might start by, you're thinking, well, what's the cardinality of this set? And you might start listing elements, e to the 1, e to the 2, e to the 3, where n can be any natural number. And you might think to yourself, well, hey, I can pair up each element in this set with the natural number that it's raised to, right? And so, to say this a little bit formally, there's a bijection between S and the natural numbers. Okay, and how can we see this intuitively with a picture? Well, our first set on top could be n, so 1, 2, 3, 4, etc. And then our set S is going to be these e to the n's. So e to the 1, e to the 2, e to the 3, etc. And we can see that there's a natural way to pair these guys up. Okay, so S is the same size as the natural numbers because we can list all the elements of S. We can count them. And so how do we say that with a function? So here's the notation. We have a function f. We're going to send something in the natural numbers to something in S. And the way that we're going to do that is exactly what I'm illustrating here with these arrows. We're going to take something in n, and we're going to send it to e to the n, okay? So that everybody in S gets hit. So I send 1 to e to the 1, I send 2 to e to the 2, etc., and that's exactly what I illustrated here. Now, in some of the homework problems, I'm going to ask you that the bijection that you're given, the function f that you're giving, is actually a bijection, and we have to check two things. Now, I'm not going to check that all of these examples that we're doing are injective and surjective. It's going to become obvious the more examples that you do, and if this is obvious to you, then you can skip around. But so this is what f is doing, right? And we can say, okay, well, this means that f of n is equal to e to the n, and we claim that f is a bijection. Okay, we're trying to show those sets are the same size, so we need to show that that function that's sending n to e to the n is actually a bijection. Okay, so first, show injection. And do you remember how to do that? Right, we want to show that if you have two outputs, and they're the same, then the corresponding inputs have to be the same, right? So we cannot have two different inputs matching to the same output is what injection means. Okay, so for example, I think I gave this before, x squared is not injective because it fails the horizontal line test. We have the same output corresponding to two different inputs, okay? All right, so for the first, we're going to show injective. Need to show that if f of n1 equals f of n2, then n1 had better equal n2. Okay? So suppose f of n1 equals f of n2, then by definition of f, we have e to the n1 equals e to the n2. We know that the natural log undoes the exponential e function, and so if I apply ln to both sides of this equation, of course, this undoes the e, and so we get n1 equals n2, and therefore f is injective. Okay, so now show surjection. Okay, so we want to show that for all y in our set, need to show, so for all y that's getting hit in our set, for all y in S, there exists some k in the natural numbers. So in our set here, so that f of k is equal to y. And you know, these surjection things aren't too bad, but you know, it might help to show scratch work if you need it, but I don't think we need it for this one. Okay, so suppose y is in S. Now, anything in S is of the form e to the n, where n is a natural number. That was just the definition of S. Okay, so suppose y in S, then by definition of S, y is equal to e to the k for some k in the naturals. Okay? Therefore, f of k is equal to e to the k, and so we're done. Okay, so we have found a k in n so that f of k is equal to y. Okay, so that's what surjective means. Okay, so now let's talk about countable. Okay, so a couple definitions for countable, some ways that you can think about it. A set is countable if it's either finite, okay, you can literally count the elements, or there's a bijection with the elements in the set and the natural numbers. So in this case, with our S here, we know that S is countable because we constructed this bijection F so that there was a direct correspondence between between n and S. Okay, so every natural number gets hooked up with somebody in S. Okay, so S was countable in that example. Here's an easy way to think about countability, because this isn't always the most useful definition, but intuitively, you can think that a set is countable if you can list the elements. So I gave it a star here because it's important. So can you actually write the elements down? Like theoretically, if you could write forever, could you write the elements down? If yes, the set is countable. If no, it's uncountable. So of course, every finite set is countable by definition. We can literally list each element in this set S, 1, 2, 3, and 4. And same thing with this finite set A. We can list all of these elements, no problem. Even with infinite sets, like I was mentioning, you can always, like if you can theoretically list the elements forever, then the set's countable. We call infinite sets that are countable countably infinite. And so here's some examples. If my set is the natural numbers, I have 1, 2, 3, 4, 5, 6, and theoretically, I can keep going forever and ever. Theoretically, I can make this list go forever and ever. Same thing with the integers. I can say, okay, well, I can list them. I can say, well, I have 0, I have -1, I have -2, I have -3, and theoretically I can go that way forever. And also theoretically I can start listing them this way forever. Okay, so the integers are also countable, all right? Now the last countable set that I'm gonna mention on this slide is the rational numbers. I'm gonna prove this towards the end of the lecture, that the rational numbers are actually countable as well, countably infinite. And even though the lists may not be as like nice as these lists, we can still theoretically list all of the elements from Q. We can say, well, there's 1/1, there's 1/2, there's 1/3, blah, 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 blah. We can say that there's 2/1, 2/2, 2/3, 2/4, 2/5. We're going to get some duplicates, blah, blah, blah. But we don't really have an issue with finding, like, we would be able to theoretically list every rational number. And again, we're going to prove this towards the end of the video. But that's the idea here. So the naturals, the integers, and Q, the rationals, these are all countable sets. They all have the same cardinality, which means there exists a bijection between all of them. We're going to list an explicit bijection between N and Z, but I don't think we're going to do one between Z and Q, but I want to say your book maybe does this one, but anyway, it's really the same idea that we're going to be playing with for to show that Q is countable. Okay, now what about the real numbers? So you cannot theoretically list the real numbers forever and ever and ever. There's no pattern, rhyme, or reason to the real numbers, right? I mean, you know, there's no like all possible combinations that can be listed for decimal expansions. There's weird things with no pattern. Like you don't just have numbers 0, 1, 2, 3, 4, right? And I mean that you could say, oh well, you know, they're countable, right? Decimals of this form. But, you know, you could have weird things happen like non-pattern decimal expansions. And so there's no way to theoretically list every single real number. There's just no way. And again, we're going to show this towards the end of the lecture, but it's kind of a really remarkable fact that honestly, I would say this kind of stuff really got me into math when I first learned it. Like, I think I learned it in a discrete math class, but I was just like, this is some crazy stuff. But yeah, okay. So the real numbers are not countable. So here's another countably infinite set that you might not expect. It's going to be the Cartesian product of the natural numbers with themselves. Okay, so all that means is that in the first slot, of our ordered pair, we're going to have a natural number, and in the second slot, we'll have a natural number. And so the idea here is we need to figure out some kind of bijection between this set and the natural numbers. And it's not so easy to write an explicit bijection out for this, but we can certainly describe one, okay? And so what I want you to think about is matrices, right? So like if we have an n by m matrix, or rather if we have entries, let's see, maybe I'll do it off to the side here. Entries in a matrix. Okay, because the idea here is that we're like tacking on a different dimension, so we need some kind of way to describe where these points live. Okay, so entries of a matrix are going to be of the form A n m, where n is row, m is column. So just as a reminder, something like A23 means that this element is in the second row, third column of the matrix. Okay, and so the idea is that we can write elements in the set in matrix form, right? We can say, oh, well, look at A11 is going to be 1, 1. A first row, second column is going to be 1, 2. Okay. I'm just going to write a few of these out so that we can see what's happening here when we try to construct a bijection. Maybe I'll write this. Actually, I'm going to erase this, so I have more room here. And this thing is going to go on and on because natural numbers go on and on. Okay, second row, first column, 2, 2. Second row, second column. Oops, I didn't mean to write 2, 2 there. I meant to write 2, 1. Here's 2, 2. And so forth. Okay, so I'm going to write just a couple more of these so you see the pattern. I should have probably written this before, whatever. Whatever. Okay. Alright, so this continues on horizontally and vertically. Okay, so this is our matrix representation of this set here. Okay, and so we need to construct a bijection to show that we can list all of these elements. And so the idea here, I mean, there's a few different ways you can do this, but the idea here is let's start with this as natural number 1, okay, and then go here so that this is natural number 2, and then turn back to the diagonal. Say, okay, I'm going to map this here so that this is natural number 3, okay, and then I'm going to go down to show that this is natural number 4, and then I'm going to go back up the diagonal. So the idea is go down the diagonal, go up the diagonal, snake down the diagonal, snake up the diagonal. And this is going to make sure that everybody's hit once, okay? And so thus showing there's a bijection between this set and the natural numbers. Okay, so this is number 4. So now we're going to snake back up and say this is number 5. This is number 6. This is number 7. Snake back down. This is 8. This is 9. 10. Okay, this goes down to 11, and it snakes back up, okay? And you can see that everybody's going to get hit. So, yeah, it's a little bit tedious to write an explicit bijection here. I think that's kind of a hard exercise, but you can if you really want to. But I think this picture illustrates it pretty well, how you can always loop around going up and down the diagonals to hit everybody in your matrix. Hence, the thing is countable. Okay, so I'm just going to list some facts here without proof, and then we'll prove some of these things. So the naturals, the rationals, and the integers, as I mentioned, are all countably infinite. So they're the same infinite size, and that is the easiest infinity that we can understand. And they call it olive knot, and not like an olive knot, haha, but no, it's like, I don't know, there's a symbol, but it's called olive knot. I think this is how, I'm gonna screw it up, but it's called olive knot. It's like the smallest level of infinity. And then there's olive 1, and then there's olive 2, and so forth. But we're not gonna really get into that because let's just keep our sanity for this semester. But if you're interested, you can really go down a rabbit hole and learn about these things. But yeah, so okay, yeah. So these are all countably infinite. The reals are uncountably infinite, and so that means that there's no bijection between the naturals and the reals. And in fact, we can say that the reals are strictly larger than the naturals. And I said that the naturals were size olive knot, but actually you would think, okay, well, are the reals size olive 1? But no, that's not the case. Anyway, it's a weird theory that I don't know enough about to explain, but if you're interested, you should look it up. Okay. Any set S for which the cardinality of the set is the cardinality of the natural numbers is countably infinite. So if we can construct a bijection, just like we did with the e to the n example with our S, if we can construct a bijection from the set to the natural numbers, then that set's countably infinite. So here's some weird facts that we're going to prove. You're going to prove this last one in the homework, but this is, to me, when I first learned this, I was like, what are you talking about? So, hence the what the hell in the parentheses here. The cardinality of the open interval from 0 to 1 is the same cardinality of the reals, okay? So, like, just let that blow your mind for a second if you haven't really heard about this. I think maybe a lot of you have, but whatever. So here's negative infinity to infinity, and you're telling me that this tiny little portion of the real numbers, which to scale you wouldn't even be able to represent pictorially, but here's 0 to 1, and so you're telling me that this interval has the same size as the real numbers? What? Are you kidding me? I don't know. I think that's insane, okay? And we're going to show this. We're going to show that we can construct an explicit bijection from 0, 1 to the reals. In fact, any open interval, the cardinality of any open interval is equal to the cardinality of the reals, no matter how small, okay? That is mind-boggling, okay? You can take something that is like, you know, like you wouldn't even be able to imagine how small it is, and it's the same cardinality as the reals. Like, that is insane. Okay, and then in the homework, you're going to show that the cardinality of the open interval from 0 to infinity is the same as the cardinality of the reals. Still a shocking fact, but not as shocking as the second fact, I don't think. But yeah, so that's what we're going to do. Okay, I want to say that maybe you guys have probably heard of this, but this this is the Hilbert Hotel paradox, okay? So here's the idea. You have, and this is how like people sort of start by teaching they teach the cardinality of the naturals with this funny example. So you have this hotel, okay? And the idea here is that there's no vacancy, that every single room is occupied by someone or a family or whatever. But for our purposes, let's just say it's one person. And this infinite hotel goes on forever. So it's in bijection with the natural numbers. You have room 1, 2, 3, 4, 5, 6, and 7, and it goes on and on and on and on. And there's no vacancies. Okay? So the first question you want to ask is, do we have room for one more guest? And the answer is, well, yeah, we do. We can just shift everyone in room N to room N plus 1. So, sure. This is an infinite hotel, right? So we can say, well, I'm just going to shift everybody in room N to room N plus 1. So shift everyone in room N to room N plus 1. And then room 1, by effect, is open for the new guest that comes in. Okay? So what about if we have 2 more guests? What if we have 100 more guests? Well, the same trick works. If we have 2 more guests, we can just shift the guy in room, or the girl, in room N to room N plus 2, and then effectively making the first 2 rooms open for the next 2 guests that come. And same thing if 100 guests come. Remember, we have an infinite hotel. We can do this shift for whatever finite number we want. So if 100 guests turn up, then we can say, okay, so take the guy in room N and move him to room N plus 100. And so we have 100 open rooms for these new guests. Okay, so now what happens if countably infinite more guests turn up at the hotel? How in the world are we going to accommodate them? Well, this is no problem, okay? Because we can just move the person in room N to room 2N. So, for instance, the guest in room 1 goes to room 2, the guest in room 2 goes to room 4, guest in room 3 goes to room 6, and so forth. And so guess what? We've made room for this countably infinite number of guests that just turned up because we can just stick them in the odd rooms. Now all of the even rooms are full, but the odd rooms are empty because we moved everybody into an even room. So what's the point here? So the point is that N is the same size as N union finite set. Okay, that's from the first 2 examples. Okay, that's what we're learning here, that the size of the naturals is the same size as I just had a brain fart. The naturals are the same size as the naturals union some finite set. So, we can still fit everybody in a room, even if we're adding 100 more people or so. And so, the next lesson here is that because we had a countably infinite number of people show up, and we were still able to fit them in N rooms, Okay, we also learned from this that the size of the naturals is the size of the odd naturals and the even naturals. And that cardinality of n is equal to n union n. Okay, so if we tack on a countable set, then so if we have a countable set and we tack on another countable set, it's gonna be countable no matter what. Okay, so that's the point of this. There's also here's another one to think about. What if we have countably infinite buses with countably infinite people in each bus? Can we accommodate them in Hilbert's hotel that is now, it's completely full? Someone's in room 1, 2, 3, 4, etc., starting from the beginning. Can we accommodate countably infinite buses with countably many people? And the answer, weirdly enough, is yes. How are we going to do this? Well, we're going to take the person, so everyone, the rooms are occupied, right? So we're going to take the person in room N and we're going to send them to room 2 to the N. Okay? And so now what that means is that all of the rooms, since 2 to the N, since 2 is prime, this means that all of the rooms of 3 to the N, 5 to the N, 7 to the N, those are all going to be empty after this shift happens, after everyone in room N moves to room 2 to the N. And Euclid showed in the Elements, the book, that there are infinitely many primes. And I'm running out of room, so I'm going to erase this and write it up here. So Euclid showed that there are infinitely many primes, and so what we're going to do is now everybody in the hotel has shifted to room 2 to the N, okay? And so we said, room 3, room 9, room 5, room 25, all of these rooms are open, okay? So here's our first bus with the countably infinitely many people, okay? And remember, there's countably infinitely many buses. And so what I'm going to do with the first person in the first bus is I'm going to send that person to room 3 to the 1. I'm going to send the next person to room 3 to the 2. These are all open, right? Because everybody that was in the hotels in room 2 to the N for some N. I'm going to put the person in room 3 and 3 to the 3. And so there's no overlap here because 3 is prime, okay? Then I'm going to go to the next bus, okay? And I'm going to go to the next prime, which is 5. I'm going to send person 1 to room 5 to the 1, person 2, room 5 to the 2, etc., etc. And I'm going to keep playing this game because there's infinitely many primes I can pair everybody up with. Okay? So that was a lot. Anyway, I like this little story. Okay? So the big point here is that countably infinite sets are really nice. Really strange still, but pretty much the nicest type of infinity we can deal with. Okay, so let's do some examples. Using the bijection principle, show that the cardinalities are the same. Okay, so the first set that we're looking at is the set N, and the natural numbers, if you will, and we want to show that it has the same cardinality as the natural numbers minus 1, okay? So this is going to be equal to the set N without 1. Okay? So how do we do this? We need to find a function, right? We need to find a function that goes from the natural numbers to the natural numbers minus 1 or vice versa. And so we're going to define a function from the natural numbers to the natural numbers without 1. And how are we going to pair all of these things up? Well, I mean, if you put your n on top, we can see the pairing pretty clearly, I think. So we're going to send 1 to 2, we're going to send 2 to 3, 3 to 4, etc. Okay, so in general, we're going to send n to n plus 1. So f of n is equal to n plus 1. This is a bijection. I think it's clear, it might be clear why it's a bijection, but just to beat a dead horse, I do that sometimes, so you can skip over things that are clear to you. But just in case people want to see lots of examples. So here's the injection. So we want to suppose f of n1 is equal to f of n2. Then, by definition of f, n1 plus 1 equals n2 plus 1. So subtracting 1, we get n1 equals n2. Okay, so surjective. So to show for all n prime in the naturals without 1, there exists some n in the naturals with f of n is equal to n prime. Okay, and so the idea here is that f of n is just simply n plus 1, and we're trying to solve for n. So we get n equals n prime minus 1. Let me just... So this is the scratch work. I'm just going to circle this. It's not really part of our proof. So here's our proof. Let n prime in n without 1 be given. Choose n in the naturals such that n is equal to n prime minus 1, right? We're given an n prime. We can find the little n by just sticking in the n prime. And notice that there's no problem here because n prime was in n without 1, so we're never going to get, like we're never going to have 1 here and give us a contradiction. We can't have little n be 0 or something. Right? Little n prime is going to be bigger than or equal to 2. Okay, so then then f of n is equal to n prime. Okay? Okay, wait, did I do this right? Let's see, okay. I'm just looking at this and I'm like, wait a minute, what? Okay, so let's see. Let's just make sure what we did. Okay, so we're solving for little n. Let n be n prime minus 1. So then f of n prime minus 1 is just equal to, by our definition of f, yeah, okay, yep. Sometimes I overthink things too. Okay, so thus F is surjective. And so, since F is both injective and surjective, it follows that F is bijective. And hence, since we found a bijection between the naturals and the naturals without 1, that means these two sets are the same size. Okay, same cardinality. Okay, let's do that the natural numbers are as big as the even natural numbers. Okay, and so this isn't too hard to show. So how are we going to do it? How are we going to pair every natural number up with the even numbers? Well, we can say maybe we'll send every natural number to 2 times that number. Okay, so we're going to send n to 2 times little n and check. So you check that F is injective and 2, F is surjective. And that'll show you that the natural numbers have the same cardinality as the even natural numbers, which is kind of a weird idea, right? That so the even naturals are a subset of the naturals, and so like a subset of a set has the same size of that set. It's kind of a strange idea. But yeah, that's the idea here. Okay, so next let's prove that the natural numbers and the integers have the same cardinality, i.e. the integers are countable. Okay, so let's kind of figure out a way to see what our map has to be. So map question mark. So if I write the integers on top, here's -2 continuing on forever in the left direction, 0, 1, 2, 3 continuing forever in the right direction. I want to map every integer onto a distinct natural number. Like I want a bijection here. And so maybe I could send -2 to 4. I could send -1 to 2. I could send 0 to 0. I could send 1 to 1. I could send 2 to 3. I could send 3 to 5. And so the idea, if you can see it, is that I'm mapping all of the negative integers to even natural numbers. I'm mapping 0 to itself, and then I'm mapping the positive integers with odd natural numbers. Okay, so I want to describe that with a function. Okay, so I want to go from the integers to n, and there's a few different, there's ways to do this a different way. But what I'm going to do is I'm going to send something in the integers, and I want to write exactly what I have described here in math form. So what do I want to do? Well, I have 2 cases to deal with, right? So I need a piecewise function. The first case is if my integer is 0 or negative, really. And then my second case is if my integer is positive. Where am I going to map that to? So first case is if I'm less than or equal to 0. And the second case is if my integer is strictly bigger than 0. So like I said, if it's less than or equal to 0, I want to make sure they go to the even natural numbers. And so to account for the negatives that those integers are giving me, I'm going to send every x that is less than or equal to 0 to -2x. Okay? That way 0 gets sent to 0, -1 gets sent to +2, etc. And then I want to send if it's bigger than 0, if my integer is bigger than 0, I want to send it to all the odd integers. So I want to send it to 2x minus 1, okay? And you can play with it and check it. When I plug in x is 1, I get 1. When x is 2, I get 3, and so forth. So this is my bijection, okay? So bijection is, we're going from z to n, and we have f of x is equal to negative 2x for x is less than or equal to 0, and 2x minus 1 for x is bigger than 0. So I'm never going to be in a situation over here where I'm not a natural number, because I fixed that with the negative sign. Okay, so I want to actually prove that this is a bijection. And am I out of room? Yeah, I'm out of room. So I'm going to just erase stuff. Because this might be a little bit more complicated because it's piecewise. Not too much more complicated, but maybe a little bit. Okay, so to show f is a bijection, we need to show first f is injective. Okay, so let f of x1 equal f of x2. Well, we have two different cases of where our x1s and x2s could be, okay? So the first case is both of these guys are less than or equal to 0. Both are negative. Then we have, by the definition of our piecewise function, negative 2x1 equals negative 2x2. Do the stuff. You guys know what to do. x1 equals x2. Done. Case 2. Could we possibly have... actually, so I just want to say that 1 is bigger than or equal to 0, and 1 is... I want to say 1 is bigger than 0, and I want to say 1 is less than or equal to 0. And this is really the same no matter what I label the one as x1 and x2 as. And when you're trying to say that, you want to say without loss of generality, or without loss of generality, meaning that this trick works no matter what I choose x1 or x2 to be in this case. And sometimes I'll abbreviate WLOG, okay? So without loss of generality, suppose that x1 is less than or equal to 0, and x2 is bigger than 0. Well, then, by the rule of our function, we have negative 2x1 equals 2x2 minus 1. Okay, so I think I pulled a chord out, so let me continue. So this might sound weird when it's all pieced together, but anyway, okay, so negative 2x. Okay, so this can't happen, right? We can't have an even number equaling an odd number, okay? And so this case 2 doesn't even exist. Okay, so forget it. Case 3, both of these guys are bigger than 0. And that means that we have, when f of x1 equals f of x2, we have 2x1 minus 1 equals 2x2 minus 2, and you can easily show that this implies x1 equals x2. So in any case, f is injective. Okay, and so as an exercise, you should show that f is surjective to complete the proof. Okay, let's go to this one. All right, so the interval from 0 to 2 is the same size as the interval from 0 to 1. Again, really kind of a weird idea that this interval right here is the same cardinality as this interval right here. Kind of strange, but let's prove it's true. And so here's the idea. When you're trying to prove that these two intervals have the same cardinality, I'm just going to write this out. Create a bijective function such that 0, 1, that either 0, 1 or 0, 2 is the domain, while the other is the range. Like, you want to draw the picture first, I think, before you start writing the bijection. I think that's really helpful when you're doing these kinds of problems. So one of these, the 0 or the 1 or the 0, 2, make that the domain and make the other one the range. And so when I draw this, I'm going to draw, well, I'm just going to say, well, let's let 0, 1 be the domain. So I'm going to say this is my 0, 1 is the domain. And I'll let the 0, 2 be the range. So here's 2 right here. And I want some kind of function to cover all of this. Okay, and linear things are bijections. They map intervals onto intervals. So yeah, whenever you're trying to map an interval onto another interval, linear functions are good for this when your endpoints are real numbers. Okay, so what is this function? Well, you know from whenever you took pre-algebra or whatever that this line here has a slope of 2 and a y-intercept of 0. So this line is just 2x. And that's the bijection we're looking for. Okay. Now you could also do something, you could also have drawn your picture differently and maybe done something like this. You could have switched up your endpoints so that 0, 1 was on the y-axis and 0, 2 was here. There's lots of different ways to show that these two intervals have a bijection between them, but this is just the way that I wanted to do it with this guy right here. Okay, so let f, so where are we going and where are we coming from and where are we going? We're coming from the x values, we're coming from 0 to 1, and we're going from 0 to 2. We're mapping into the y values. Okay, so we're going to let f go from 0, 1 to 0, 2. And what are we doing? We're sending something in 0, 1 to something in 0, 2 by this function, 2x. F of x equals 2x. So injective and surjective, you can check this. So check that f is injective and surjective. So you know the story here. Show that for injectivity, show that if 2x1 equals 2x2, then x1 equals x2. That's not too crazy to show. And then show that if you have any y in 0, 2, there exists some x in 0, 1, such that f of x equals y. So that's it. F of x equals... I keep hitting the damn cord, so if the video looks weird and cut in weird spots, it's because the frickin' cord keeps getting detached from my microphone. Let's try this one. Okay, so pause the video, try it yourself, see if you can do it. I always like to draw a picture. So we're trying to show that one of these is the range, or let's start with one being the range, one being the domain. So I'm just going to pick, and you don't have to pick it like this, but I'm going to pick 0, 1 as my domain, and I'm trying to map it into negative pi over 2 to pi over 2. I want to show that these intervals have the same cardinality through some isomorphism. Oh, sorry, some bijection. Just forget I said that. Okay. So what's it going to be? Well, I can do a linear one just like I did before. You don't have to do a linear one, but I think that's kind of the easiest way to show that two intervals are the same when you have real numbers as your endpoints. So maybe I'll do something like this, and then here so that everybody in 0, 1 gets mapped to somebody in negative pi over 2 to pi over 2. Okay, and so this is just a linear function, and you guys know how to find linear functions. This guy has a slope of pi and a y-intercept of negative pi over 2. So this is our bijection. All right, so yeah. I'm going to skip the injective because I really feel like I've just done too many of those examples, but you should show it. Let's show surjectivity. So, want to show. What do we want to show? Okay, so our function f, let's be careful about how we write this. We're going from 0 to 1. And we're mapping into negative pi over 2 to pi over 2. Okay, and we're sending x to this linear function through this linear function pi x minus pi over 2. Okay, so we want to show that everybody in the output is getting hit, okay, by something in the input under the map. So, want to show for all y in negative pi over 2 to pi over 2, there exists an x in 0, 1 such that it gets sent to the y under the map, such that f of x is equal to y. Okay, that's what we're trying to show. So again, with the surjective stuff, I like to do some scratch work before I start writing the proof. There's like some backhand work to check. And so I just want to do f of x equals y. So f of x is pi x minus pi over 2. And I want to set that equal to y. I'm trying to figure out the x that makes that true. So I need to solve for x here. And so I'll do that. Okay, so I'm just solving for x. I want to be a little bit careful. Okay, so I get x is this. Now make sure that x actually lives where we want it to live. Where did we want x to live? We wanted x to live in 0 to 1. Now make sure x is in 0, 1. Okay? Well, how do we do that? X is in terms of y, and we know that y is between negative pi over 2 and pi over 2. This is still scratch work, by the way. Since y is between negative pi over 2 and pi over 2, if I do some trick or some manipulation here, I can figure out, if this actually lives in 0, 1. So divide by pi. Y over pi is bigger than 1/2. Negative 1 over 2. And then add a half. So y over pi plus a half, just adding a half to everybody, gives me exactly what I wanted. Okay, so this x does indeed live in 0, 1. Check. Now the actual proof. Now the proof. So that was all scratch work and color. Now we're getting back to the proof. Let y be a negative pi over 2 to pi over 2. Yeah, I think that's all I wanted to say about the scratch work. Okay. That's fine. Okay, so now let y be in this interval. Choose x in 0, 1 as x equal y over pi plus 1/2. So here's the game. I give you a y, you give me a corresponding x. Okay? Then f of x is equal to f of y over pi plus 1/2. And what does f telling me to do? It's telling me to send my input to pi times the input minus pi over 2. Okay, so I just get y, all right? Hence, f is surjective. And we're done. So once you show injectivity, we've shown surjectivity, therefore f is a bijection, both injective and surjective. Okay, so let's prove a more general result, and that is that the interval 0, 1 is actually, it has the same cardinality of any interval where m and n are real numbers. Okay, so no matter how small you make m and n, it's still going to be the same cardinality as 0, 1. So again, you're just doing the same picture here to get your intuition of what the function should be. So I'm just going to choose 0, 1 to be the domain, and it's going to map into m to n right here. And so you can just draw your line. I mean, you don't have to do a line, but again, I think it's the easiest in this case. So you want everything here to get mapped to everything here. Okay, and so if you find your slope and your y-intercept, you're going to see that your slope is n minus m. And of course, you can see from the picture that your y-intercept is m. Is a bijection from 0, 1 to mn. And I'm going to leave this as an exercise for you to check. Okay, let's do some more examples. So we have 0, infinity, and negative infinity 3. So again, I like to draw a picture. One is my domain, one is my range. And so I'm going to say, okay, well, maybe I want my domain to be from 0 to infinity. And so I'll have this going from 0 to infinity, and I'll have my range going from negative infinity to 3. So maybe something like this. So this is going from negative infinity to 3 is my range of just this picture that I drew. All right, so what is the line here? Well, I don't really have another, it doesn't matter what your slope is, right? I could have easily drawn something else like this, right? Or I could have drawn something even wider like that. It doesn't really matter what your slope is. So for the sake of simplicity, I'm going to say the slope's negative 1, right? We know the slope is negative, but the magnitude of it, I don't really care. So let f of x be negative x plus 3, right? I have my y-intercept at 3. So we're going from a domain of 0 to infinity to a range of negative infinity to 3. And so I'm going to send something in my domain to something in my range via this map. Okay? Now, easy exercise. Show injective and surjective. Yeah. Okay, so Not too bad. What about this one? Okay, so we want to match up a domain and range with these two intervals that we're given. So let's do something that's not linear. Let's look at what should we do? Well, maybe we could have some type of like function with an asymptote, right? And so maybe I'm going from 0 to 1 on my x-axis, and I'm going from 0 to infinity on my y-axis. So maybe it looks something like this, right? And so I have an asymptote at x equals 0. And so the idea here is, like, I know that this function looks like 1 over x, but it's shifted so that it hits x equals 1 here, right? And so we could say that our function f of x, well, let's actually say where it's coming from and where it's going. So it's coming from 0 to 1, and it's going from 0 to infinity. And I'm going to send something in 0, 1, not including 1, to 1 over x minus 1. Okay, so that's what I drew here in purple. So again, you can check that on these intervals. That's the key thing, guys. The intervals, right? It's not this thing, if we were defining it from the real numbers to the real numbers, it certainly wouldn't be surjective because there's an asymptote at 0, right? Like, we can never hit all the real numbers, but because we're restricting our intervals, the input interval from 0 to 1 and our output from 0 to infinity, everybody that needs to get hit gets hit in 0 to infinity, but not including 0. Okay? So, check on these intervals that f is bijective. So just use what we've done before. Okay, I'm like looking, let's see. Okay, so you could do a linear bijection, like a bijective linear function here. I think it would be more natural to see that, to remember your trig and say, okay, well, I know that, like, trig functions are defined in terms of, like, these radian values, like pi over 2, 3 pi over 2, stuff like that. And I know that without any kind of transformations, the range for these trig functions go from -1 to 1. So it might be natural to consider a trig function here. So if I draw my picture, I'm going from, well, actually I'm going to include it here, pi over 2 to 3 pi over 2, with a range from -1 to 1. Okay? And so this can easily be accomplished with the sine function. So if we let f be in this interval, and we're going into -1 to 1, send something in pi over 2 to 3 pi over 2 to sine of x, right? And normally, you know, this function, if, again, like, this is the importance of restricting the intervals. If you're just drawing out this function, we know that it's not, it's certainly not injective, right? We have something like that or whatever. And so we definitely don't have injectivity, but along this interval we do, because the period of sine is pi, 2 pi, but notice that pi over 2 and 3 pi over 2 are only pi apart. So there's no problem here. We're not going to get like a hump or anything with where injectivity fails. So our sine function, if we're going from pi over 2 to 3 pi over 2, we're starting at 1. At pi, we're going to have 0, and we're going all the way to 3 pi over 2, which is at -1. And so this is our curve representing f, and not hard to argue that this thing is injective and surjective, so I will refrain from doing that here. Okay, so let's go ahead and look at this one. So we want a range and a domain to be -1, 1, and the reals. So if I draw a picture to get some intuition for what my function should be, I am going to let my domain be from -1 to 1. So maybe like that. And I want everybody to get hit in this domain. So I want my y values to extend infinitely down below and infinitely down above. So, so maybe something like this. Okay. And the question is, what kind of function can I write that gives me what I need here? Well, I can, to get from positive infinity here, negative infinity here, I can incorporate some asymptotes here. So I can say that there's an asymptote at -1 and 1. And so the thing is, like, maybe I can build my function and say, okay, well, I know I have an asymptote at -1, and I know I have one at 1, so maybe that can be my denominator here. And then you can mess around with the numerator. 1 is not going to work because that gives you like a disconnected piece, which we don't want. But x will actually work here. If we just mess around with the numerator a bit and put x here, this function will do the job. It will give us this picture, and yeah, for this one, I'm not going to prove, again, the injective, surjective stuff, but maybe I will for the next problem. So our function, we're going from -1 to 1 to the reals, and we're going to define our function. Something in -1 to 1 is going to get mapped to x over x plus 1 times x minus 1. And that will do the job. I'm not going to check it's injective and surjective, but you can do that if you want. Okay, so here we have cardinality of -infinity to infinity, which is the same thing as the cardinality of R, right? And we want to show that it's same cardinality as 2 to infinity. Okay, so I'm thinking about logarithms because I know that logarithms can have a restricted domain depending on where it is, whether it's shifted or what. So I know from college algebra that with logarithms, if this is x equals 2, then I've drawn a picture where the domain goes from 2 to infinity and the range is everything. So this is a log function. So let f go from 2 to infinity. Remember, 1 has to be the domain, 1 has to be the range. Doesn't matter whether it's on the left or the right. Right here. And so this is the natural log with a shift. And so we can say that x in 2 to infinity is going to go to ln of x minus 2. Okay. And so f is a bijection yeah, I mean, same kind of trick as before. So for injective, suppose ln x1 minus 2 equals ln of x2 minus 2, and then we use the e the exponential to get rid of the ln. So raising both sides to the e gives me x1 minus 2 equals x2 minus 2, blah, 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 x1 equals x2. Okay, so that's injective, and then surjective isn't hard to show either. Okay, so here's the remarkable fact that I said what the hell in the beginning of the lecture. So we've shown a lot of things, and I'm going to use the things that we've shown to prove this remarkable fact that the cardinality of the reals is the same cardinality as the open interval from 0 to 1. And so I'm going to use a homework problem that you may not have done yet, but I think it's easier this way. So by homework 2, by homework 3. By homework 3, problem 2C, cardinality is transitive. And what does that mean? Whenever cardinality of A equals cardinality of B, and cardinality of B equals cardinality of C, then cardinality of A is equal to cardinality of C. Okay, so transitive. By example 5, so by example number 5, we saw that the interval from 0 to 1 was equal to negative pi over 2 to pi over 2. And we claim that negative pi over 2 to pi over 2 is equal to the cardinality of the reals. And then once we have that, we'll be able to say by transitivity that the cardinality of the reals is same as the cardinality of 0, 1. Okay, so this one is not too bad. We have negative pi over 2 to pi over 2. I'm not good at drawing symmetric things, but there it is. And we want everybody to get hit in the range. So we want something like this, maybe. And what does this remind you of? The tangent function, right? So this is the tangent function. So let f from negative pi over 2 to pi over 2 into the real numbers be defined by the tangent function. So we're going to send something in negative pi over 2 to pi over 2 to tangent of x. And this is, again, not hard to show that this is bijective, but for the sake of not repeating myself too many times, we're not going to show that here. But now, assuming that this is bijective, so cardinality of negative pi over 2 to pi over 2 is equal to the cardinality of R. And since we know that cardinality of negative pi over 2 to pi over 2 is also equal to cardinality of 0 to 1, then by transitivity, it follows that 0, 1, cardinality of 0, 1 is equal to the cardinality of the reals. And that's crazy. Okay, so the next theorem we're going to look at is we're going to show that the rational numbers are countable. And so it's going to be a similar story to how we showed that the Cartesian product of the natural numbers n by n was countable. And so what we're going to do here is we're just going to show that the positive rationals are countable, and it's easy to adapt the proof to show that the negative rationals are also countable. And from previous exercise, we know that the union of two countable sets is countable. And so Q plus union Q minus is Q. If each piece is countable, Q is countable. Okay? So, again, we're going to make a picture like this. We're going to have an infinite grid where we start with our number 1, we go to 2 over 1, 3 over 1, and so forth. And then the next level of the 1 being in the numerator is 2 being in the denominator. So 1 over 2, 1 over 3, 1 over 4, and you guys can see this pattern. So this is how we're going to arrange our infinite list of positive rational numbers. And there are going to be some duplicate numbers in our list, but we don't really care, because if we show that this infinite list, even with the duplicates, is countable, if you remove some elements from a countable set, it's still going to be countable. So like once we take out the duplicates, it's still going to be countable. And so the idea here is that we're going to do the snake thing like we did for the n by n case, for the naturals by naturals case. And so we're going to start and we're going to say this is n equals 1. So this is my first element in my set. We're trying to show that this grid is in bijection with the natural numbers. So this is number 1. This is number 2. We don't want to keep going horizontally because then we're never going to get to, say, 1/2. So we need to snake around just like we did before. We need to snake around the diagonal. So 1 over 1 goes to 2 over 1, and let's send 2 over 1 to 1 over 2. Okay, and then we'll send 1 over 2 to 1 over 3, and then we'll start snaking down the diagonal. 1 over 3 to 2 over 2 to 3 over 1. And then we'll again snake along going back up. So we'll go to 4 over 1, 3 over 2, 2 over 3, 1 over 4, 1 over 5, snake back down, and so forth. So, it's not a super, like, airtight proof, but it makes sense that when you go along the diagonal like this, we're never going to miss a fraction. We're never going to miss a rational number. And so, since we can list the rationals with this snaking diagram, Q plus is in bijection with the natural numbers. Remember that being in bijection with the natural numbers just means that you can list these, and you can list them just as I was listing them before. So this is number 1, this is number 2, this is number 3, this is number 4, this is number 5, this is number 6, and so forth, okay? So that's the idea. That is why the rational numbers are countable. Okay, so here's the big theorem, and that is that the real numbers are not countable. And so we're going to use an argument called Cantor's diagonalization argument. Okay, so I mentioned at the beginning of the video that that George Cantor thought a lot about infinity, and so he was the first one that people know who proved this. Okay, so here's what we're going to do. We'll show 0, 1 is not countable. Now, in a previous slide, we showed that the cardinality of 0, 1 is the same as the cardinality of the reals. So if we can show that 0, 1 is not countable, then we know that the reals aren't countable either. Okay? So to show 0, 1 is uncountable, we'll show that a subset of 0, 1 is uncountable. Right? Because if a subset of a set is uncountable, then the whole set has to be uncountable. You can't have a countable set containing uncountably many elements. It's not, doesn't make any sense. So let this subset be called A. I'm going to call it A. And this is going to be X in our set 0, 1, so that the decimal expansion of X only consists of 2s and 3s. Okay, so this is a very specific subset that I'm saying, but it's a subset nonetheless, right? And you can really, you could play this game with 2 and 4, 5 and 6, whatever, but I'm just going to use 2 and 3. And so what I'm going to do, so I'm going to show that A is uncountable, and to do that, I'm going to proceed by contradiction, and I'm going to suppose that it's countable. So what does it mean to be countable? It means that I can list the elements, right? The elements are in bijection with the natural numbers, so I can list them. So I can list the elements in A. So I can say, okay, here's x1, x2, x3, x4, all of these are so all of these numbers have decimal expansions only consisting of 2s and 3s, and they're between 0 and 1. So what could I say that these numbers look like? Well, I could just say, okay, I don't know what x1 really looks like, but it's something like this, like 0.3222322, I don't know, okay? Just something like that. Just something with an expansion of only 3s and 2s. And maybe the next one is something like this, 0.2232333, I don't know, okay? Maybe the next one is something like this. Okay, who knows? So here's the crazy trick, okay? So I'm supposing that that A is countable, and I know that all of my elements in A are going to look something like this. Maybe not exactly this, but I know that the decimal expansions are only going to contain 2s and 3s. And so the clever idea that Cantor had was, he said, well, how about I show that this list is not countable by constructing something that's not in the list. Okay, so I claim that, all of A is going to be in this list, hence countable. A is countable, but I'm going to show you that I can actually create something that's not in the list. Okay, how are we going to do it? So I claim that I can find an X in A which is not in our list. Okay, so how are we going to construct such an X? Well, we know it has to contain 2's and 3's, but here's the trick, okay? What I'm going to do is I'm going to look at my first element, and I'm going to change, if it's a 3, I'm going to change it to a 2. Okay, so I'm going to, in this case, I'm going to change 3 to a 2. And then I'm going to move down to the second element, and I'm going to look in its second slot, and I'm going to change that number. So since it's a 2, I'm going to make it a 3. Okay, and so forth. I'm going to look at the third slot here, and I'm going to say, okay, that's a 2, I'm going to change it to a 3, and I can keep playing this game. And so I have found an element that is not in my set, right? Because I can keep doing this forever and ever. I can look at the fourth slot, and I can change, if it's a 2, I can change it to a 3. If it's a 3, I can change it to a 2, etc. And therefore, X is not equal to anything in our list for all I in n. That's how we're going to index this. So why can't x1 be equal to x? Well, I've changed the first digit. Whatever it is, I'm changing it. So it definitely can't be equal to that. Why can't it be equal to x2? Well, I'm changing the second digit from the second digit in x2 and so forth, okay? So therefore A is not countable. We claimed it was. We said, okay, it's countable. I can list all of the elements in A. x1, x2, x3, x4, x5, and so on and so forth. But I have found an element that is in A that's not in my list. Okay, so A is not countable. Since A is not countable, or uncountable rather, this implies that the bigger set that it's sitting in, which is 0, 1, is uncountable. And we've already shown that the cardinality of 0, 1 is equal to the cardinality of R. So this implies that R is uncountable. And this is also crazy. But yeah, I hope you guys enjoyed the video. Thanks for watching, and I'll see you guys next time.